Okay, so all right. So today we're going to learn about something else you can do with the second derivative test. So far for maximum and minimum points, we have just learned the first derivative test. And the first derivative test was that we had an equation, we took the derivative, we made a sign line, and anytime we saw the derivative switch from positive to negative, that was a maximum. If we saw the derivative switch from negative to positive, that was a minimum. So that is my default usually for finding maximum and minimum points. That's what I usually try first whenever I'm doing these problems. However, there are some ways that they can ask problems where the first derivative test will not work. So it is important for us to also know the second derivative test for maximum and minimum points. So the second derivative test tells us that when the first derivative equals 0, so we're looking at places where our first derivative equals 0. If f double prime of c is greater than 0, that means that the function is concave up, so f of c would have to be a minimum. So if you want to kind of like sketch a little picture of what's happening there, if you know you have a derivative of a first derivative of 0, that tells you have a horizontal tangent. And if the second derivative is positive, that tells you that you have something that's concave up. Well, the only way you can have something concave up that has a horizontal tangent is for that to be a minimum point. Right? Now, I sometimes get these a little bit mixed up because you have a positive second derivative and a minimum. Positive makes me want to think maximum. It is backwards. Sometimes I draw this picture right here to help myself remember that if I have something concave up, then it would have to have a minimum point there, not a maximum. Okay? If your second derivative here is negative, that tells you the original function is concave down. So if you're looking at a function that is concave down, then the only place that you're going to have a first derivative that is 0 is at that maximum point. So whenever you have a function that's concave down and a first derivative that is 0, you're going to have a relative maximum at that point. Now, one of the reasons I don't like second derivative tests is if you find the second derivative is also 0, then the test fails. It does not tell you whether this is a maximum or minimum. You would have to go back and do the first derivative test anyway. So I prefer using the first derivative test whenever you can, but you will have to use the second derivative test in some instances, and we'll see that in these notes. The first derivative test is what we have already done. I'll show you on this next problem here. So if you have a question that looks like this, it says find the relative extrema for this function. Okay, this does not specifically say you have to use a second derivative test, so you could do a first derivative test. Let me show you what the first derivative test looks like, and then I'll show you what the second derivative test looks like. So for first derivative test,
I'm not sure I understand.
So this is the one we have already done. First derivative test, you take the first derivative. So you've got f prime of x is going to equal 6x squared minus 5x minus 4. You need to find the places where that derivative equals 0. So you will set this equal to 0. And that's not the easiest factoring there. Let's see if I have 3x and 2x. Could I do a minus 4 here and a plus 1? So that give me negative 5. That'll give me negative 8x. Positive 3x. That'll give me the negative 5 that I need. So that's how you factor that one. So that's a little more difficult factoring. It even took me a while. You've got to guess and check on that one, right? So you got your numbers that multiply to give you 6x squared. I chose 3x and 2x. You could try 6x and 1x, but it's not going to work. And then for 4, you could use 2 and 2 or 4 and 1. It ends up being 4 and 1, and you have to have your 4 here, your 1 here, because if you multiply it back here, you'll get negative 8 and a positive 3. But you pretty much just have to guess and check, right, for those. And so that would give us, switch back to a pen, 3x minus 4 equals 0, so 3x equals 4, x equals 4/3. And here we'll have 2x plus 1 equals 0, so 2x equals negative 1, so x equals negative 1/2. So for this, we need to if we're doing first derivative test, so this is what we've already done. If we're doing first derivative test, we make a sign line. And we put negative 1/2 here, and we put 4/3 here. And we are trying to plug into the first derivative. And I'm going to make the chart, so I'm going to put my 3x minus 4 here and my 2x plus 1 here. So the 3x minus 4, let's see, this would give me a negative, 0 would give me a negative, anything bigger than 4/3 will give me a positive. For the 2x plus 1, I'll get negative here, positive, positive. So I'm looking at positive, negative, positive. And so for first derivative test, you would say, if we're looking for extrema, you would say that f of x has a relative maximum at x equals negative 1/2 because f prime of x switches from positive to negative. And then you would also say f of x has a relative minimum at x equals 4/3 because f prime of x switches from negative to positive. So this is what we have already done. That is first derivative test. It still works. If I solve this problem, that's probably the way I would do it. But we need to learn the second derivative test as well. On your homework, these questions are going to look, they'll look kind of like this because that's the way your book asks them. And I'm going to make you use second derivative test tonight and tonight only because that is what we're practicing. But a lot of these questions could be done with first derivative test. So we have already done this as first derivative test. You can tell these maximum and minimums without looking at the second derivative at all. Right? So this is still valid, but we're also going to learn another way to do these problems. Okay. Now you can decide whether you like it better or worse. It doesn't matter, but there are some ways that we'll see where they can ask the problem a certain way where you've got to do it this way. So let's look at what it would look like with the second derivative test. So for the second derivative test, okay, when you do a second derivative, you still have to do the first part the same, which is why I prefer to just go ahead and do the first derivative test. So you would still take the first derivative, and you would get 6x squared minus 5x minus 4. You still have to find the critical points, okay? So that equals 0. At least we've already factored it, right? We got 3x minus 4 times 2x plus 1 equals 0. And so we get x equals 4/3 and x equals negative 1/2, right? I'm not spending much time on that because we've already done it. So you still have to do this because you have to know that the first derivative equals 0 to use the second derivative test. But now, rather than do a sign line, this is what we do for the second derivative test. So this is where it starts to be different. We're going to take the second derivative. So we're going to do f double prime of x, which is not bad on this because it's a very simple second derivative, right? We got, well, if I can multiply, we'll get 12. 12x minus 5. Okay, that is your second derivative. And what you want to do is you want to test your critical points to see what your second derivative is at that point. So you're going to plug in f double prime of negative 1/2, which would be 12 times negative 1/2 minus 5. And so that'll give you negative 6 minus 5, which is negative 11. And we're also going to test 4/3. And we will get 12 times 4/3 minus 5, which is going to be, let's see, that's over 1. We could cancel, make that a 4. So 1, 16 minus 5, which equals positive 11. Okay, so for this, what this is telling us is that at 4/3 and negative 1/2, we have a horizontal tangent because our derivative is 0, right? Our second derivative, if I have a second derivative of negative 11 at that point, what does that tell us about the original graph? What does second derivative tell us about the original graph? Concavity, and since I have negative 11, this is concave down, right? Which means I'm looking at a graph that looks like this, which means I've got a maximum point. And then at 4/3, I've got a positive 11 for my second derivative, so that tells me that we're concave up at that point. So that's going to look like this, which tells me I have a minimum point. Okay, so using the second derivative test, your conclusion is going to be different. You can say, so f of x has a relative maximum at x equals negative 1/2 because our first derivative at that point, and to show it's at that point, do f prime of negative 1/2 equals 0 and f double prime of negative 1/2. I would not say equals negative 11 because you need to definitely have the work where you show that it equals negative 11. But here you need to show them that you know the sign of that is what matters, not the value but the sign. So that is less than 0. Now you could go on to explain this further. You could say which means that f of x is concave down at that point, so it has to be a maximum. You could go on to say more, but you don't have to. The second derivative, you need to say, so for second derivative test, you got to show that first derivative is 0, and the second derivative is either positive or negative at that point. Okay, and then our conclusion for the minimum point would be f of x has a relative minimum at x equals 4/3 because f prime of 4/3 equals 0 and f double prime of 4/3 is greater than 0. The cleanest way to write this is to put f prime of 4/3. That means the derivative, first derivative at 4/3. It is acceptable to say f prime of x equals 0 and f double prime of x is greater than 0. But if you do that, you must say at x equals 4/3. You have to show it's at that point because it is not true that this is always 0, right? So you must make sure you're showing it's at that point. I like to just do f prime of 4/3. That means the derivative at that point, and then you don't have to use as many words for that. Okay, questions? So if you were to see this question on a free response question, these are both valid ways to answer it. You could use first derivative test, or you could use second derivative test, and both are valid ways, and you would get full credit for those. I, on the homework, want you to use second derivative test tonight, because that's what we're practicing, right? That's what we've got. That's what we're trying to learn how to do right now. But beyond tonight, you can use either one if there's enough information to use either one. So just whichever one you prefer. Okay, questions? Okay, so let's use second derivative test for example. Did I skip from? Oh, I totally skipped example 1. We're not going to go back and do that. It was a simple example. Totally skipped it. Sorry. All right, we're going to do example 3. All right, so we're going to use second derivative test, even though we could use either one. So we're going to do f prime of x, and we will get negative 15x to the 4th plus 15x squared. And although you don't have to make a sign line, you do still have to find critical points for this. So how am I going to solve that? What could I do? Take out a 15x squared. So if I take out a 15x squared, I'll have negative x squared plus 1 equals 0. So I will have 15x squared equals 0, and I'll have negative x squared plus 1 equals 0. So I will get, here I'll just get x equals 0 whenever I solve that. Here I will get 1 equals my x squared. I will square root both sides, and I will get x equals plus or minus 1. So either way, you have to do your critical points. If you wanted to do first derivative test, here is where you would make your sign line for that. But we're practicing second derivative test, so I'm going to slide this over here so I got more room. So let's find our second derivative, and we would have negative 60 x to the 3rd plus 30 x to the 1st power. And so now I have to find f double prime of all of my critical points. So I'm going to do negative 1. We'll get negative 60 times negative 1 to the third plus 30 times negative 1. That is going to give me positive 60 minus 30. So I get 30 for that. I've got f double prime of 0. Here's why I don't like second derivative test. What do you get when you do f double prime of 0? 0. Ugh. And then f double prime of 1 will be negative 60 times 1 plus 30 times 1, which is going to give us negative 60 plus 30, which will be negative 30. Now, here is another reason I do not like second derivative tests, because it has just failed at 0. And if it fails at a point, then you have to go back and do first derivative test, which is why I would rather just do first derivative test in the first place. But we could go ahead and make conclusions about negative 1 and 1. So at 30, this is positive. Our second derivative is positive, which tells me concave up, which means it looks like this, which means I have a minimum. At positive 1, I've got a negative second derivative, which tells me that the graph is concave down, which means it looks like this, which means I have a maximum. I write those things down a lot of times, or at least think of them in my head. I like to write them down, so I make sure I've got that correct. So we would say f of x has a relative minimum at x equals negative 1, because, so for second derivative test, the two things that have to be true is you have to have the first derivative at that point, so f prime of negative 1 has to equal 0, and the second derivative, so f double prime of negative 1 has to be positive or negative. In this case, it is positive, which means that you're going to have a relative minimum. We could also say f of x has a relative maximum at x equals positive 1, because f prime of 1 equals 0, and f double prime of 1 is less than 0. Or you could say is negative if you don't like the signs. But this does not tell us anything about 0. So what we have to do for this is we've got to go back to the first derivative and do the first derivative test anyway. Which again, is why I don't like doing second derivative test unless I have to. To decide if we have a maximum or minimum at 0, we're going to have to make a sign line anyway. So we got negative 1, 0, and 1. And you can do your chart if you want. You got 15x squared, and you got negative x squared plus 1. It's really like a straightforward chart because you're really only testing that negative x squared plus 1 because 15x squared is positive everywhere. And really, I only care about these points right here next to 0. So if you don't want to test these out here, you don't really have to. If I plug in something like negative 1/2, negative 1/2 squared plus 1. When I square here, I'm going to get rid of the negative that's on the inside of the parentheses. It's going to be 1/4, but the negative on the outside stays there. However, this is still smaller than 1, so you'll get a positive here. And then if I plug in positive 1/2, it really doesn't change anything. You still get negative 1/4 plus 1. So you'll still get a positive here. So you don't even really have to check these points over here. You would have a negative here and a negative here if you did. So that tells you negative, positive, positive, negative. So do we have a maximum or minimum at 0? We do not. So we would have neither at 0. Sometimes the problems will tell you to test all critical points and tell whether you have a maximum, minimum, or neither. This one just asks for extrema, so you wouldn't have to make a conclusion about that. But you do need to test it because sometimes you do have a maximum or minimum at that point also. Okay, questions? Okay, so let's look at the reason that we have to learn this, because so far I've done nothing but tell you I don't like second derivative test and that I would just use the first derivative test anyway. So let's look at example 4. Let f be a function such that f of negative 1 equals 1. At each point xy on the graph, f is the slope given by, has the slope given by this. Which of the following statements is true? So we're looking for a relative minimum at negative 1, a relative maximum at negative 1, neither one, or there's insufficient information. Okay, so although it doesn't say consider negative 1, all your answer choices let you know negative 1 is the point we care about, right? Are we going to be able to make a sign line for an implicitly defined function? Can you make a sign line with like negative 1 right here whenever you've got x's and y's you would have to plug in? You cannot, okay, because you got x's and y's. So we're going to have to use second derivative tests on this because you can't make a sign line for implicitly defined functions. So the first thing you need to do is check to see if the first derivative equals 0. If the first derivative does not equal 0, you do not have a point here. So they gave you f of 1 equals negative 1. So that means the point we're looking at is negative 1, 1. All right, so they gave you the y-coordinate that goes with this. So dy dx such that xy equals negative 1, 1 would be negative 1 squared minus negative 1 times 1 plus 1 squared minus 1. And so just be careful right here. This square right here gets rid of the negative on the inside of the parentheses. It does not get rid of the negative on the outside. So you got negative 1 plus 1 plus 1 minus 1. That does give you 0. Okay, so first derivative equals 0. So that's the first step in the second derivative test. Now we need to look at the sign of the second derivative at that point. So we're going to have to take the second derivative. So we will have d squared y squared. Okay, so second derivative is going to be negative 2x minus, what do I have to use to take that derivative in the middle? Product rule. So I'm going to put some parentheses. I got to do x times dy dx plus y times 1. And I'll have plus 2y dy dx. And then that minus 1 will just become 0. Now, you could simplify this here by putting that dy dx in, like putting all of that there. It's going to make a mess if you do that. But all we care about is this one point that they have asked us about, this negative 1, 1. So I'm going to go ahead and plug this in. So xy equals negative 1, 1. And so I will have negative 2 times negative 1 minus negative 1. What is dy dx at this point? It's 0. So I'm going to plug in 0 for my dy dx. Plus 1 times 1 plus 2 times 1 times 0. So I'll get positive 2 minus, that's going to be 0 plus 1, so I'll just be minus 1 plus 0, so I'll get 1. So, a positive second derivative. What does that tell us? Concave up, which means it looks like this, which means what do I have at that point? Minimum. So it would be A, would be your answer for that. So here is an example where second derivative test has to be used. You cannot use first derivative test on this problem. So while we may not have to use it on everything, we are going to have to use it at times. Okay, questions on that? Okay, let's look at a couple more that are examples that you might see where you have to use this. So, let f be a twice differentiable function. Selected values of f prime and f are shown in the table above. Which of the following statements are true? 1 is f has neither a relative minimum nor a relative maximum at x equals 1. 2 is f has a relative maximum at x equals 1. 3 is f has a relative maximum at x equals x equals 4 here. So 1 and 4 are where we care, what we care about, right? Now, it appears right here that, so we're looking at, the reason we're looking at 1 and 4 is because our derivative equals 0 right here. If you try to do first derivative test for this, can you make a sign line for this? Like, if we tried a first derivative test sign line, we'd have like 1 here and 4 here. So we'll look at that first derivative. Our first derivative test below 1, what do we have? Positive or negative? It looks like it's negative. What do we have between 1 and 4? We got negative and positive, right? So what has happened, and we can't put like positive and negative on here. So what has happened here, they have given us a table. It doesn't have everything, right? So that tells me like somewhere in here, we had another critical point. If this is, it's a twice differentiable function, so it's continuous. So there was another critical point somewhere here between 2 and 3. There could have been multiple critical points between 2 and 3 because we don't have all of the points. It could be going back and forth like crazy. So we can't do a sign line for this because we don't have all of the information. Some of the questions that we've seen like this, they'll tell you, we've given you all the critical points. We've given you everywhere that the derivative equals 0. They definitely did not here because we can't go from negative 1 to 5 without crossing 0. So first derivative test is useless on this one. It does not help us. So we have to use second derivative test. So we want to look at the second derivative. Right here it is negative. That tells me this is concave down. Looks like this. What do I have if my graph is concave down? Maximum or minimum? Maximum point. So at 1 we should have a maximum, so 2 should be correct. And then at 4 I have, I'm going to look at my second derivative. This is concave down, which is going to, I'm sorry, I don't know why I put down. Losing my mind. Concave up, which looks like this, which means what do we have at 4? Minimum. So, this would be wrong because it says there's a maximum. It's also false for 1 because 1 and 2 can't be true at the same time anyway. So B would be your answer for that. Okay, questions? All right, let's look at another one. f is a twice differentiable function with which of the following statements are individually sufficient to conclude that x equals 2 is the location of the absolute maximum on the interval from -5 to 5. Okay, so if we know the derivative at 2 equals 0, is that enough to decide that we have a maximum or minimum point? If we just know derivative equals 0. So if our derivative equals 0, that means it's a critical point. Are critical points always maximums or minimums? They are not. Sometimes they're nothing, right? Sometimes they are neither maximums nor minimums. So 1 is out. It is not enough alone to verify that we have, it is not enough alone to verify that we have a maximum at that point. All right, let's see, we are looking at absolute maximum, so that changes a couple of things. All right, so x equals 2 is the only critical point on f from -5 to 5, and f double prime of 2 is less than 0. So this is second derivative situation. If x equals 2 is a critical point on f, then that is a place where our derivative is 0 or undefined, but in this case, since we're twice differentiable, it's going to be 0. So critical point on f, that's basically the same as saying as our f prime of 2 is 0. So that's our first step of second derivative test. Then it tells us that f double prime is less than 0. So if I have a negative second derivative means that I am concave down, which means that my graph looks like this, which means that I have a maximum. But this alone, like second derivative test, only guarantees a relative. Do we have enough information to say it's absolute? Okay, let's think about it for a minute. Okay, we're looking at a graph here from -5 to 5, right? There is only one critical point, and it happens right here at 2. It's the only place that it happens. So if that is my only critical point, that means my graph has to do something like this. Because if I'm concave down here, I would have to switch to concave up somewhere to get another critical point, right? If that's my only critical point, if I switch to concave up and increasing where this goes back up, then I would have to have another critical point there, right? So since that's my only critical point, it's got to be endpoints or that critical point. And because this is concave down, it has to be that absolute maximum. So C is already out. It could be A. It could also be D. So our other option is that x equals 2 is the only critical point, and f of -5 is less than f of 5, which is less than f of 2. That is not second derivative test. That is simply we would like plug in our endpoints and our critical point, right? So if it's our only critical point, f of -5 might be something like -2, and f of 5 might be something like 1, and f of 2 might be something like 3. We just test our endpoints and our critical points, right? I'm just making up numbers here to kind of remind ourselves of what we did for that. So f of -5 is the lowest, f of 5 is lower than is a little bigger than that, but still lower than f of 2. F of 2 is the biggest number on that interval, right? So this also shows that you would have a absolute maximum at that point. So this would be your like first derivative test where you're testing those points. This would be your second derivative test, and they are both sufficient information. One alone is not that. Okay. Questions? Okay. So your assignment tonight is, let me make sure this is what I want. We've got 37, 41, 43, 44, 45, and 53. Yep, that looks good. And I want you doing second derivative tests on all of these. Our book doesn't have a lot of questions that like force you to do second derivative tests. I want you to do second derivative tests on all of these problems. It is, I won't force you to do it any other time, but we need to practice second derivative tests. So you got about 10 minutes to go ahead and get started on those. And